Good afternoon. In today's video, I will walk you through the complete design and implementation of a fully functional corporate network developed across multiple cities in Mexico. This network integrates LAN, WAN, MPLS, VLAN segmentation, OSPF dynamic routing, DHCP services, public internet access through NAT, and custom security schemes using ACLS. Everything I will show you today is supported by the official documents produced during the project, such as the physical design, logical addressing, routing configuration, and final proof of concept. So let's get started. So let's begin with the first section, which is the network physical design. To begin, let's look at the physical design of the network. This is the real-world representation of how offices, production centers, routers, switches, and end devices are physically interconnected. This company operates across several cities: Mexico City headquarters, Guadalajara office and production center, Monterrey office, Saltillo production center, Querétaro office and production center, León office, Silao production center. Each site follows a simple yet scalable LAN topology: one router, one switch, and multiple end devices such as PCs, servers, and printers. These are grouped inside color zones as shown in the Cisco diagram. First, in light blue, we have the Silao production center. Then in a deeper blue, we have the León office. Then in a light green, we have the Saltillo production center, and in a deeper green, the Monterrey office. Then in a kinda of red color, we have the Querétaro office. Then in a pink or reddish color, we have the Querétaro production center. In purple, we have the Guadalajara office, and in a lighter purple, we have the GDL production center. These networks are not isolated. They are interconnected using serial PPP1 links. Each office is directly paired with its production center. For instance, here we have the Guadalajara office connects to the Guadalajara production center, which is this one, as shown in this image. This physical design mirrors how a real enterprise will structure its multi-city IT infrastructure: dedicated LANs at each location, which control it site to site, links facilitating communication across all the organization. Understanding this physical layout is essential before diving into a logical addressing or routing. The diagrams allow us to visualize how packets will traverse from one office to another through serial links and MPLS cloud. Where the design becomes more interesting is in the interconnection of cities. The offices and production centers are linked using PPP serial WAN connections, which simulate real point-to-point listed lines between remote sites. Each office is paired with one production center. As I said before, Guadalajara with Guadalajara Production Center, Monterrey, Saltillo, Querétaro Production Center, and León, Silao. These pairs form a basic backbone of the corporate network. Communication between headquarters and all other remote sites occurs through these structured links, forming a hub and spoke style topology, but with a distributed traffic pattern suitable for enterprises environment. The use of /3 subnets for these links ensures efficient address allocation while clearly identifying them as a point-to-point connections. This is a typical approach in the real enterprises ones, because these links only require two usable IP addresses, one for each router. Although the physical structure is similar, each building fulfills a different operational role. Corporate offices host employees' computers, local servers, printers, and internal services such as Wi-Fi access points, while production centers host specialized equipment used for manufacturing, agricultural monitoring, or industrial processes. This includes sensors, barcode readers, production servers, and other OT devices. This distinction is directly reflected in the way each site is physically arranged. Production environments typically require more reliable connection to sensor devices, while offices need a connection for employees and administrative functions. The full physical topology of uses color code zones to visually distinguish each city. Each site. This is extremely useful when presenting and analyzing large-scale networks because it allows us to visualize map which devices belong to which city at a glance. As mentioned, in this case, in a light blue color, we have the Silao Production Center. In a deeper blue, we have Lion Office. In a light green, we have Saltillo Production Center. In a deeper green, we have Monterrey Office. In red, we have the Querétaro Office. In a pinkish reddish color, we have the Production Center, Querétaro Production Center. In a purple color, we have the Guadalajara Office. And in a bluish purple, we have the Guadalajara Production Center. So let's begin with the second section, which is the logical design of the network. Now that we have covered the physical layout of the corporate network, let's move into the logical design. This is where the network takes shape from an addressing and segmentation perspective. If the physical design tells us how devices are connected, the logical design tells us how they communicate. The goal of the logical design is to create a consistent addressing scheme, a clear segmentation of users types and devices, predictable routing behavior, and scalability for future growth. Because the company has multiple cities, each with offices and production centers, the logical design ensures that every location follows the same structural rules, even though the services may vary. The entire corporate network is built around the private IP range. Wait a minute, I will make a little more zoom into the table. The entire corporate network is built around the IP range 172.16.0.0/16. Rather than dividing this space randomly, each city receives its own /16 block. This approach has two advantages: consistency, every site follows the same internal structure, and scalability, because each location can grow without redesigning the whole network. Within each /16 block, subnets are assigned to the required VLANs. To maintain uniformity, every site uses the same VLAN IDs. VLAN 10 servers or IoT, VLAN 20 employees, VLAN 30 guests or OT depending on office or production center, and VLAN 99, which is the management. This uniform numbering allows the network team to identify device's role immediately by simply looking at its IP range or VLAN assignment. And although every city uses the same VLAN IDs, the specific subnet differs based on their local /16 block. For example, one city might assign 172.16.1.x networks, and another might use 172.16.2 and X. Production center with sensors and equipment may have tighter subnets, such as /27 or /28, to allocate only the needed number of addresses. This balance between standardization and customization makes the network both organized and efficient. Beyond internal VLANs, the logical design also defines the point-to-point WAN links that connect offices to production centers. This uses /30 subnets, which provide exactly two usable IPs, perfect for router-to-router links. Using /30s minimizes waste of IP space, makes it easy to identify WAN interfaces, and keep routing tables clean and readable. For example, each office production pair gets a dedicated /30 link, ensuring clarity in route advertisement later during OSPF the deployment. One of the strengths of this logical design is that every city uses the same internal structure, regardless of location or size. This means VLAN 10 always represents servers, VLAN 20 always represents employee, workstation, and wireless AP, and VLAN 99 always isolates administrative traffic. Production centers always segment sensors separated from employees and core services. This level of consistency is extremely valuable when scaling an enterprise network. If a new location were added tomorrow, the same template could be applied instantly, reducing the design time and configuration errors. The logical design reserves enough space for around 30% growth, ensuring new devices, users, servers, and even entire new VLANs can be added without restructuring the whole network. This means the company can add more sensors in production centers, increase the number of employees, add new services, expand Wi-Fi coverage, create new subnets if needed, all without renumbering or redesign the entire topology. To summarize, the logical design accomplishes several key objectives. It divides the company entire address space into structured, predictable blocks. It standardizes VLANs across all cities. It uses efficient /30 networks for WAN links. It provides ample room for growth, and it prepares the network for the routing, NAT, and security configurations that come next in the next section. This logical layer sits between the physical connections and the higher level configuration task. By having a clean and consistent structure, all subsequent steps, OSPF, DHCP, NAT, ACLs, become much more straightforward and reliable. In the next section, we will see how this logical framework is brought to life through VLANs configuration, dynamic routing, and DHCP services. Let's continue with the third section, which is the VLANs, OSPF, and DHCP. Now that we have established the physical and logical foundations of the network, the next step is transforming data structure into a functional and fully segmented environment through the configuration of VLANs, routing, and automatic IP distribution. This is where the network starts behaving like an enterprise-grade system. So let's begin with the VLAN segmentation. The entire corporate network relies on a standardized set of VLANs across all cities. VLAN 10 servers or IT services, VLAN 20 employees, VLAN 30 guests or OT devices depending on the building, and VLAN 19, which is the management. Every router and switch pair uses a router on a stick design, where one physical interface on the router is divided into multiple sub-interfaces, one per VLAN. This allows the router to access the default gateway for all devices, and enabling inter-VLAN communication while keeping traffic logically separated. The switches assign ports to the appropriate VLANs, ensuring that users, servers, and management interfaces remain fully isolated at layer 2. We have in the screen, I have an example of this case. We have the Ciudad de Mexico, CDMX case, and we can observe that the VLAN ID 10 is for Servicios CDMX, the VLAN ID 20 is for Employees CDMX, and the 99 is for Administration. Each one has her own purpose. For example, Servicios CDMX is the core server. The Employees CDMX is employees PCs and printers, also AP. And the 19 is router and switch network. In the table we can observe also the network, the mask, and the gateway for this case, which is the CDMX. To simplify client deployment, all employee VLANs rely on DHCP pools configured or on the routers. This allows automatic IP assignment, faster onboarding of new workstations, and predictable gateway and DNS settings. Meanwhile, infrastructure devices, servers, printers, APS, and sensors use static addressing, ensuring critical services are always reachable at known IPs. This combination of static and dynamic addressing strikes a balance between flexibility for users and stability for essential systems. Once VLANs are active, the next challenge is connecting all cities so they can reach each other. For this, the network uses the OSPF routing protocol, configured consistently across every router. All routers participate in a OSPF Area 0, enabling them to share information about their subnet and automatically learn the route to every other office and production center. This protocol, OSPF, provides fast convergence if a link goes down, automatic route distribution, eliminating the need for dozens of static routes, and scalability, allowing the network to grow seamlessly. This is crucial in a multi-city design, where routing changes need to propagate quickly and reliable. With VLANs segmenting traffic inside each building, DHCP simplifying IP location, and OSPF linking all cities through dynamic routing, the corporate network becomes a single interconnected system. From this point on, any employees in any city can reach the company internal services. Production centers, devices can communicate back to their parent offices. All locations participate in a unified addressing and routing framework, and the groundwork is set for NAT, MPLS, and security rules that will come in the next section. This section marks the transition from isolated buildings into an integrated wide area infrastructure. With this configuration complete, the network is now fully functional internally. In the next section, we will connect the corporate world to the outside world through NAT, public addressing, and MPLS integration. Let's continue with the fourth section. In this section, where I will be explaining the NAT and MPLS integration. Now the internal network is fully segmented and dynamically routed. The next step is enabling communication with the outside world. This is where NAT and the MPLS based one come into play. These two components serve very different purposes, but together they allow the company infrastructure to extend beyond the boundaries of each building. The MPLS cloud acts as the primary transport network, linking all corporate sites together instead of relying on a complex mesh of direct connections. Each office and production center connects to MPLS, provided through a simple point-to-point link. This provides several benefits. First, efficiency routing between any two sites, isolation from public internet traffic, consistent latency and predictable forwarding, a scalable foundation that can support additional office on production centers in the future. Because our routers participating in the same OSPF domain, once a route is injected at one location, it immediately becomes available across the entire MPLS connected infrastructure. In practical terms, this means a sensor in a production center can instantly reach a server in a different city, and employees can access resources company-wide without any special static routing rules. While MPLS handles the internal communication, NAT handles the external one. Corporate devices cannot use private IP addresses on the public internet, so network address translation is used at every office to reach internal private networks with the outside world. This includes two main NAT strategies. First, static NAT, or one-to-one translation. This is used to publish each production center server to a unique public IP address. Each location exposes a different service, such as HTTPS, HTTP, or FTP, using a fixed mapping between an internal private IP and a global routable public IP. This allows external clients, partners, or monitoring systems to reach the company's servers securely and predictably. Employee VLANs use port addresses translation, which is a dynamic NAT with overload, or PAT, meaning dozens of or hundreds of user devices can share a single public IP when accessing the internet. This is perfect for everyday office activity, browsing, software updates, external communication, and cloud tools. It minimizes public IP usage and simplifies the management. Each office includes a small simulate ISP router to emulate the real behavior of an internal service provider. This device is responsible for assigning the public IP ranges, forwarding external traffic towards the corporate routers, accepting outbound traffic from NAT, and representing the next hop to the internet. With this setup, NAT is not just simulated, it behaves exactly as it would in a real enterprise environment, making the testing process realistically and reliable. When MPLS and NAT work together, the MPLS cloud handles internal private traffic between cities. NAT handles external public-facing communication. OSPF automatically ensures routes are known across all locations. Each office controls what is exposed to the internet. Production centers can publish their servers securely. Employees can access the web using PAT, and the entire system remains isolated, secure, and scalable. At this stage, the company achieves the full connectivity, both internally through MPLS and externally through NAT. With routing established and public access enabled, the network is almost complete. The final layer involves securing this section through ACLS and policy restrictions, and that's exactly what we will explore in the next section. Let's begin with the fifth section and the final one, which is the security schemes. With internal connectivity established and external access configured, there is one final step before the corporate network can be considered complete, which is implementing security controls. This is where access control lists, or ACLS, come into play. These rules determine exactly what kind of traffic is allowed into the network from the outside and which traffic must be blocked. Every office publishes at least one core service to the internet, either an HTTP web server or an FTP server located in its production center. Without protection, those servers will be exposed to all types of incoming traffic, including unauthorized and potential harmful connections. To prevent this, each router applies an inbound ACL on its one interface, the interface facing the ISP. This ensures that only the traffic needed for the published service can enter the network. For example, in this case, we have the CDMX headquarters. In CDMX headquarters, we implemented an extended ACL called CDMX infilter, applied inbound on the one interface serial 010 that points to the ICP. This ACL allows only HTTP, which is the port 80, and HTTPS, port 443. Traffic towards the public IP of the CDMX server, which is 152.78.211.10. Any other IP traffic with the destination is denied, and all remaining traffic is allowed. The server is published using a static NAT from the internal IP 172.16.0.2 to 152.78.211.10, and the rest of the office hosts use dynamic NAT overload to reach the internet. In this case, in the report, I'm presenting the connectivity test. We use ping to the IP from a PC from the PC0 in CDMX to the server CDMX, and we can observe once we have applied the ACL, we can reach from this IP to the server, and we did the same with the FTP and the HTTP. In this case, the Cisco Packet Tracer, where we have like a page, example page. Then, each site enforces a different set of allowed protocols depending on the service it provides. For web servers, only the following are allowed, as I mentioned before. In the port 80, the HTTPS, in the port 443, the HTTPS, and ICMP for basic diagnostics. Every else, SSH, Telnet, SMB, or no protocols is automatically blocked. For FTP servers, allowed traffic includes port 21 FTP control, port 20 FTP data transfer, and ICMP for ping test. Again, allowed traffic directed at the server public address is denied. This granularity ensures that the server is only reachable in the exact way it was intended to be, dramatically reducing the attack space. These ACLs follow a simple but powerful logic. Permit specific traffic to the server's public IP, deny any other traffic headed to the same IP. Allow everything else to avoid disrupting the internal or outbound traffic. Placing the ACLs inbound on the WAN's interface ensures the unwanted traffic never enters the internal network at all. This is the same method used in real enterprises, filtering traffic at the edge before it becomes a problem. With ACLs in place, each performs a verification step, as I showed you in the screen before. Can internal user reach their local server? The first example, it can. Can internal devices reach other cities through MPLS? Can internet-facing servers be accessed externally using the public IPs? And does the router correctly block traffic that should be not allowed? These tests confirm that web servers only respond to HTTP and HTTPS. FTP servers only respond to FTP. ICMP diagnostic work as intended, and all other inbound traffic is rejected. This ensures not only functionality but secure correctness. These security schemes complete the transformation from a functional network to a secure production-ready architecture. With ACLs applied, at this point the corporate infrastructure is fully built, physically, logically, and operationally and securely. And with that, we conclude the security layer of the project and complete the entire network implementation. This multi-city, multi-layer network is now fully operational, fully interconnected, and fully secured. In the final segment of this video, we will wrap up with a brief conclusion summary. So, for the final summary, in this project we designed and implemented a complete multi-city corporate network, from the physical layout of offices and production centers to a fully structured logical addressing plan, segmented VLANs, dynamic routing with OSPF, and automated IPs assignment through DHCP. We integrated MPLS to unify allocations, deployed NAT to enable controlled internet access, and applied strict ACL-based security schemes to protect every public-facing services. The result is a scalable, secure, and fully functional enterprise network that mirrors real-world infrastructure and prepares the company for future growth. Thank you for watching.